Hello everyone, my name is Satish Muleti and welcome to the show and tell demo session. Today I'm going to present a fast learning sparse array demo for automotive radars. Before going further, I would like to thank my colleagues Yarib Shavit, Jandang and Moshe Neymar and my PI, Professor Yonina Eldar. Due estimation is an important problem in many engineering applications. Here the goal is to estimate direction of far-field targets from signals received at a set of sensors. In these applications, high-resolution direction of arrival requires a large number of antenna elements. However, this increases the cost and power requirements as well as the computations since high volumes of data is generated. In particular, with respect to automotive radar application, the resources such as power are limited as most of the equipments are operating on a battery power. Hence, it is necessary to balance between these resources and the resolution, and the solution is to select the sparse array instead of using the full array. Recently, we proposed a deep learning based approach for sparse array selection problem. In the deep sparse array method, we assume that there are n antenna elements with L targets and DOs are like on a grid of m points. In this case, the signal received is given by this equation here, where A is a array steering matrix and X is a L sparse elements. The support of X is denoting the direction of arrivals and its amplitudes are denoting the amplitudes of the corresponding sources. The goal is to select K antennas out of and choose K possible choices. To achieve this, we considered a classification approach where we trained a convolutional neural network to perform this task. However, the bottleneck with the existing approach is in terms of generating the training data. In particular, for the labeling part, the method relies on an exhaustive search method, which requires queue searches and which is not scalable for large antenna elements. We propose a fast learning based solution which is much faster than the existing method. Specifically, we use submodular optimization based greedy methods for antenna selection problem. In the existing settings, we show that for selecting 10 elements out of 16, the training method is 10 times faster than the exhaustive search method. In this demo, we show the application of the proposed learning method. And further, the results show that the present method is 2 to 3 dB efficient compared to a random selection method. In terms of the hardware, the demo consists of a 16-element antenna array system that acts as a receiver. FPGA is used for transmitting the pulse and receiving the signal from antenna array. To simulate the targets, we used two dipoles, antenna elements, that transmit pulses that are received through these 16 elements. Once the 16-element target signals are received, they are fed to a deep neural network, which selects the best sparse array based on its training mechanism. The details of the hardware and the entire mechanism is present in next.
we have here is we have our receiver, which is capable of receiving 16 channels. It is based on FPGA and down conversion chains, and we can get the samples via LAN for post-processing on MATLAB. In here we have our patch array, 16 pads antenna, and we have here an independent signal generator from Rohde & Schwarz, which is based on 2 independent RF channels. Each antenna is transmitting in a different frequency at a different angle to the array antenna. Now, the sparse array is deriving the direction of arrival of those 2 transmitters, not necessarily via a 16 pads, or the phase difference of the 16 pads. Via the algorithm, we can make sure that you can, via sparse array, use not all the 16 receiving channels, using instead of 16, 10 of them, where we can derive correctly the direction of arrival of a transmitting source.